Okay, thank you, everybody. Thank you so much. This is the last seminar that we have in this seminar series for this semester. So thank you so much, all of you for taking time out of your schedule to join us. Today, we're very fortunate to have with us Professor De-Arteaga, who's an assistant professor in the Information Risk and Operation Management Department at the University of Texas at Austin. And she's also a core faculty member in the Machine Learning Lab and an affiliated affiliated faculty of Good Systems. Professor De-Arteaga holds a joint PhD in machine learning and public policy and an MSc in machine learning, both from CMU. And she has a BSc in mathematics from Universidad Nacional de Colombia. How was that pronunciation?
Okay. That's great.
Her research focuses on the risks and opportunities of using machine learning to support experts' decision in high-stakes settings, with a particular interest in algorithmic fairness and human AI collaboration. She's been featured by United Nations Women and Global Pulse and has received Best Paper Awards at NACL 2019 and Data for Policy 2016. And she's also received research awards from Google and Microsoft Research. Maria, thank you so much for being here and for being willing to share your wonderful work with her, with this audience. And we look forward to your seminar. And with that, please feel free to start whenever you're ready.
Thank you very much for the introduction, and thank you for the invitation. I'm very happy to be here. And also thank you for the service you're doing in putting together this awesome seminar series. It's really, really cool. It's been awesome to see the really great lineup of speakers that you've had. So I'm very excited to be here today. And what I'll be talking to you today about is the gap between predictions and machine learning informed decisions. Before I dive in, generally what my work focuses on is human-centered machine learning. And so part of these looks at algorithmic fairness. So in this line of work, I've studied machine learning bias and the risk of compounding injustices. Most recently, we've worked on what we term social norm bias. And so this is looking at what are some of the residual harms that remain when we mitigate fairness at a group level. I've also proposed algorithms for both enumerating biases and mitigating biases. And the other stream of my work that is naturally very interconnected is human AI collaboration. And so as part of this work, I've done research on learning to defer, who to defer to. So basically when a human and an algorithm are collaborating, when are cases where the algorithm should say, oh, I'll just defer to the human in this case. And what I'll be talking to you today about is the role of humans in the loop, and also some of the work on optimizing for constructs that matter, meaning the gap that exists between what we care about when making decisions and what we're optimizing for in predictions. And in all these, I've worked across domains. This includes child welfare, healthcare, policing, and hiring. In some of these domains, I've focused on characterizing the risks of using machine learning in these domains. That's the case of policing, for example. In some others, I've worked more along the lines of how do we use machine learning in these domains. That's the case of healthcare, for example. And the work that I'll be presenting to you today is joint work with Alexandra Sholoshova, Ricardo Fogliato, and Arthur Dubravsky. And with this, I'll dive into the research. In recent years, we have seen how machine learning is increasingly being used to assist experts in high-stakes domains. This includes assisting physicians, assisting child welfare hotline operators, and assisting hiring and recruiting managers. And often, both in research and practice, we see a focus on the algorithm as the locus of evaluation. There's a major focus on predictive performance, and in particular in constrained and static evaluation settings. And this can be viewed both in how we evaluate algorithms in research to headlines such as AI system is better than human doctors at predicting breast cancer, and AI just beat human doctors. But often we don't care about the predictions. We care about the prediction-informed decisions. And this is not just a matter of time, I argue. This is not just a matter of, oh, we're in this brief period of time in which we're using machines with supervision. There's many reasons why we would like to have human AI collaboration, and we would want to have a human in the loop. This includes the fact that often decisions are not based solely on a predictive task. Some tasks have inherent uncertainty associated to it. So that's the difference between diagnostic and prognostic tasks. And in many cases, if they concern predicting future human behavior, unless we subscribe to a notion of our destiny being written already, there's no such thing as just making decisions based on a prediction performance. There's other elements that we care about in the decision. And the criteria for making decisions can be ill-defined, contested, and may not be a perfect match for what we're optimizing for. And furthermore, there are often unobservables that the algorithm doesn't have access to, but the human does. So these are all reasons why thinking about machine learning informed decisions rather than machine predictions alone is relevant. And in today's focus will have two parts. In the first part, I'll talk about the difference between predictions and decisions. And in particular, I'll study the role of humans in the loop and the question of whether humans are capable of making good use of algorithmic recommendations to improve decisions. Everything that I just said of why we want a human in the loop hinges on the idea that the human will be able to play this role that we're putting them in. And so this question tackles one of the elements of what we need to understand in order to know if we can have this sort of desirable human AI collaboration. The second part of the talk will discuss the gap that exists between the measured construct and the relevant construct. This is another reason why considering the gap between predictions and ML-informed decisions is important, because what we optimize for is often not what we care about. And here I'll tackle the question of how do we bring the constructs that we optimize for closer to the relevant constructs. So in the first part, I'll be presenting work that we published in 2020 at CHI, and actually this week we made available the follow-up work that is now on SSRN, where we do a more in-depth analysis, and we include we extend the focus to incorporate fairness questions, and that is what I'll be presenting to you today. So when thinking about whether humans can make good use of algorithmic recommendations, there's two ends of a spectrum that are very relevant: algorithm aversion and automation bias. These are two of the main phenomena that come up as risks of why humans may not be well positioned to make good use of algorithmic recommendations. Algorithm aversion refers to undercompliance. These are cases in which the human chooses to ignore the algorithm. Often it has been studied with respect to ignoring the algorithm in favor of other human sources of information, even when the algorithm listening to the algorithm could improve the decision performance. Automation bias is on the other end of the spectrum and refers to overcompliance. And so these are cases in which we say, well, the machine is so smart, must know things I don't know, I'll just trust the machine. This was first studied in the context of high-tech cockpits, where it was found that pilots became over-reliant on the new technology and would miss heuristic cues that they would previously identify very easily. And so the question in the first part, refined, can be phrased as, are experts able to dismiss algorithmic recommendations when the tool misestimates the risk? And we study this in the context of child welfare. This is one of the domains in which algorithmic assisted decision-making is being deployed as taking the form of a risk assessment instrument, a model that estimates the likelihood that a person or case will have poor outcomes. This is widely used across domains. And this has recently been deployed by many child welfare agencies across the country. In this work, we collaborated with Allegheny County to understand how the system that they deployed was being used by the co-workers. A little bit of context of why these systems started being deployed and how they're used. It is estimated that 37.4% of children experience a Child Protective Services investigation by the age of 18 in the US. And so in numbers, that means that for a year, in this case, 2018, there are 4.3 million referrals. These are calls to Child Protective Services that have 7.8 million children associated to them. And of these, there was a result, this resulted in 3.5 million children who received investigation or alternative responses. So note that not every call receives a response. Why is that? This is the pipeline in Allegheny County, for example. Allegheny County is the county where Pittsburgh is located. So the co-worker receives a call, and they make use of historical records as well associated to the children and the family involved in a call. And based on this information, they're tasked with deciding whether the call should be screened in for investigation. In an effort to not miss flags that a child may be at risk, the amount of historical information and administrative records that are available to the co-worker has been increased drastically in the past years. And that volume of information then led agencies to turn to the question, can an algorithm tell when kids are in danger? And so the goal here was to train models that would predict the likelihood that there would be an adverse outcome. Many people have shown concern about this. So in her book, Automating Inequality, Virginia Evans devoted a whole chapter to the Allegheny County system. And the National Coalition for Child Protection Reform published a commentary titled, Pittsburgh's Child Welfare Agency Goes Full Orwell. What we study in this work is one piece of the puzzle of what we need to understand to better assess the impact of the use of these technologies in child welfare. So when the tool was deployed, the pipeline for a call that was received changed so that now, in addition to having the information in the call and access to historical records, the call worker also has access to the output of a predictive model. Note that the predictive model only has access to the historical records, not the call. And the predictive model estimates a risk score that is shown as a score between 1 and 20. And depending on details that I'll share with you in a second, it may show a screen out approval flag. This means if the co-worker wants to not screen in the call for investigation, they need a supervisor's approval. So the data, the timeline that we have is prior to 2014 was data used for development of the model. And then we have data from a pre-deployment period. This is data that was not used to train the model, but was from a period in which the model was not being used. And then we have data from when the model was being used. And the predictive model that they deployed, as I said, takes administrative records as covariates and predicts two outcomes of interest: out-of-home placement and future referral. Future referral is a future call. Since this, the county has moved away from the second outcome, but I'll talk a little bit more about that in the second part. And then these, each of these predictions gets transformed into ventiles, and the maximum of these two scores is shown as a single score if the probability of out-of-home placement is greater than or equal to 19, then a supervisor's approval flag is shown. Upon deployment, however, there was a technical glitch that led to some features being miscalculated in real time. What you're seeing here is in the x-axis, what the correct score would have been. So this is a score that we retrospectively calculate by applying the model to the features. And what you see in the y-axis was the score that was shown in real time. And so the fact that is heavily in the diagonal shows that in many cases, the score was the same or very similar, but 10% of shown scores were miscalculated by 5 or more points, and many cases that should have been flagged as mandatory screenings were not. And so in this setting, by the way, stop me anytime if you have any questions, please. In this setting, the questions that we study is first, did the deployment of the tool impact co-workers' decisions? Or was there just algorithm aversion in which they continue making decisions as they previously had? Then we ask whether co-workers treat misestimated scores differently or whether they indiscriminately adhere to recommendations. These would be a case of automation bias. And finally, we ask whether the tool's deployment and co-workers' overrides impact racial and socioeconomic disparities, and specifically how the role of the human in the loop affected things. So to tackle this question, we use these model specifications. So we do regression analysis. And so we have the assessed score, the shown score. So tildes refer to shown score and shown mandatory flags. So here what we have is the dependent variable is the co-worker screening decision. And then we consider the interaction with deployment. And in addition to that, we have indicators for whether the risk was overestimated, both the score and the mandatory flag, and underestimated. So these are cases in which either the score shown was lower than the assessed score, or there should have been a mandatory flag with respect to the assessed score, but it wasn't shown. And we have fixed effects for month, co-worker, and allegation type. This is because, for example, in different times of the year, the types of calls may be different. So with this model, we're able to study the different questions that for the third question, we'll incorporate interaction with demographic attributes. I'll discuss that in a second. But from these, we can tackle the first question, that is, well, did the deployment of the tool impact co-workers' decisions? This is a preliminary analysis where we can see that the alignment between the assessed score and screening decisions was increased post-deployment. So we can see this here in the purple line, but in particular, we can see it when looking at the mandatory flags. What we see is that post-deployment, so the purple bars, cases without a mandatory flag were less likely to be screened in. Cases with a mandatory flag were more likely to be screened in. This naturally is not allowing us to account for other factors, which is why we turn to the regression analysis. And for the first question, the coefficients that are relevant are the ones that I have in this box here. And so in this context, we ask, well, the deployment of the tool did impact co-workers. We showed that the deployment of the tool did impact co-workers' decisions. And this is what we see here, for example, the significance of the interaction between the mandatory flag and the deployment. And this shows that they did become better aligned with the score. So the deployment of the tool had an impact in the decisions. Then knowing that the behavior did change, and that is fundamental to go to the second question, because if in the second question we show, well, they don't indiscriminately adhere to the score, it could also be because they're just making decisions that are entirely orthogonal to the score. But knowing that they did change their behavior, the question is, well, was it different if the score was misestimated as a result of the glitch? What we see in this plot is we have 4 buckets of assessed score. So a given score may be underestimated, correctly estimated, or overestimated, right? And so we have buckets, and if co-workers were indiscriminately adhering to recommendations, we should see that the screening rate was the same for each one of these buckets, but what we see is very different. What we see is that cases that were underestimated were more likely to be screened in, which is the opposite of what we would expect in the presence of automation bias. And so we delve deeper, and here it's important to remember that the glitch was non-random, which is what would explain the fact that cases in which there's a lower underestimation were screening more likely if coworkers are making use of other sources of information. So what allows us to study these are this batch of coefficients. So here we have the indicator of the shown score being greater than the assessed score, shown score being less than the assessed score, and the analogous for the mandatory flags. And here we see an indication that there may be automation bias. So we see that cases where the shown score was greater than the assessed score were more likely to be screened in. But because of the non-random nature of the glitch, we need to delve deeper into this. And we do so by having a second regression in which we have the same model specification, but the dependent variable is whether the case was accepted for service after a home visit. And what we see here is that these cases were equally likely to be accepted for service. So this suggests that these screenings were warranted. And so while there's some indication here of possible automation bias, we see that the behavior with respect to the acceptance for services indicates that these cases may be different and warrant a screening. Here, we're seeing what we saw in the plot before. We see the fact that cases where the shown score was, these are less than the assessed score. So the assessed score would have been a 15, but what coworkers are seeing is a 12. This indicates that they're avoiding errors of omission because these cases are surprisingly more likely to be screened in. And what this here suggests is that they're also more likely to be accepted for service. Again, this suggests that the screening is warranted. And so basically what we're seeing here is the glitch is non-random. So cases for which that were affected by the glitch may be different. And we see that cases that were affected by the glitch and as a result, the score was underestimated, were still more likely to be accepted for service. What this indicates is that coworkers, A, are avoiding errors of omission, errors in which because the score shown is low, then they just decide to screen out the call. And what this indicates is also that they're making use of external sources of information. Oh, sorry. What this indicates here is that they're making use of external sources of information because they need to be using something else to identify that these cases are actually cases that warrant screening. And while there's some indication that there may be the presence of a mandatory flag may induce errors of commission, the magnitude of these cases is a very small set, so that does need more analysis in future work with more controlled settings. And now with this, knowing that the behavior did change, but there wasn't an indiscriminately adherence to recommendations, we asked, well, how did the tool's deployment and coworkers' overrides impact racial and socioeconomic disparities? So what we're seeing here is rates of screenings. And so we're seeing for calls where at least one of the children involved in the call is Black, what is the screening rate? And so we're seeing pre-deployment and post-deployment. And we also see what would be the screening rate if the algorithm was making decisions autonomously. And so for this, what we do is the screening rates remain the same pre and post deployment because this in large part explained because there's a constraining capacity of how many investigations can be made. And so we say, well, what if the algorithm had the same screening rate and we were just screening the top K, right? What we see is that pre-deployment, the racial disparity was such that calls with at least one Black children were more likely to be screened in. Post-deployment, these remain the same, but the algorithm would have exacerbated this disparity. There is one thing that I find very surprising here, and it's that the direction of this disparity is the same. And so I would have expected that post-deployment, there would have been a risk of this compounding. But what we see is very different. We see that it remains the same, but the algorithm in isolation would have exacerbated it. So why is this happening? To study these, we have the same model specification, but we include interactions with protected attributes. I'm going to just show you the results for race, socioeconomic status. The results are analogous, but for time, I'll just focus on one. And so we have the same model specification, but also including interactions with race. So we see here, we're seeing the coefficient for A indicates that Black children were more likely to be screened in prior to deployment. And this is what I just showed you in absolute rates, although here we're controlling for other factors. What we see post-deployment is, so this can be seen in the interaction of A with the score, deployment, and score and deployment, that the deployment did not have differential impact on screening rates. So, and coworkers' likelihood, and this one is really important, coworkers' likelihood to adhere to algorithmic recommendations did not depend on the child's race. Meaning, when we see that a human in the loop mitigates this disparity, it's not because the likelihood that they'll adhere to the recommendation is conditioned on the child's race. Instead, what this suggests is that the mitigation that we're seeing is because the human is relying on other factors of information. And so in the integration of information that is unobserved to the algorithm is what is mitigating disparities with respect to the algorithm in isolation. So to summarize, what we find is that coworkers' decisions became more aligned with algorithmic assessments after the deployment of the tool, but coworkers avoided errors of omission, performing what we term corrective overrides when the tool underestimated risk. And we find that the deployment did not affect disparities in screening rates. The likelihood of overriding recommendations did not vary across protected groups, but crucially, a human in the loop led to smaller disparities than an algorithm in isolation would have. And I'm curious whether we usually have questions throughout, or we want to leave all the questions for the end.
So I guess if there are questions, anybody has any questions, they can leave things in the chat, or
perfect.
You know, we can take things at the end. So you
Perfect.
can continue, and then if there are any questions that pop up, I can read out that question and then you can answer. Otherwise, we'll have a Q&A at the end.
Sounds great.
Yeah.
So with these, we're done with the first part of the talk that was looking at the role of humans in the loop. And one of the reasons why thinking about predictions in isolation is so different to thinking about ML-informed decisions is because how humans make use of recommendations both varies and matters. There's many domains in which what we're seeing here has been shown to be entirely different. There's cases in which humans' likelihood to adhere to recommendations varies conditioned on protected attributes, and that exacerbates biases. And so that's been the case on work looking at the use of risk assessment tools in making bail decisions, for example. And so both performance and fairness properties of the decisions may be entirely different to those of the predictions in isolation, depending on how the humans are integrating the algorithmic recommendations into their decisions. And the role of the humans in the loop, even though algorithm aversion and automation bias are real dangers, they can still be really valuable. And with this, we move to the second part of today's talk. That is, how do we bring the constructs that we optimized for closer to the constructs that are relevant to a decision? And this is work, this is a working paper that is available on arXiv. And what we study here is, so what is the usual data generating process that we use for, that gives rise to the data that we use to train a machine learning model? In this context, there's the general decisions, right, that have given rise to screenings. Under screening, we see an observed outcome, in this case, out-of-home placement. And when we're training a machine learning model, we say, we take the data that we observe, we let that be X, and then we train an algorithm to predict what the outcome is. However, the construct that arises because what we're measuring here is it's measurable, but it's a flawed proxy. And so in this context, for example, what we're measuring is what is the probability of out-of-home placement. And this is particularly for the cases that were screened in. So the intersection with selective labels is also a huge thing that I won't be going too much into the details in the talk, but I'm very happy to talk more about that in the Q&A. But what we care about really is whether the child is at risk. Why is this gap important? Because luckily, not all cases where a child is at risk result in an out-of-home placement. An out-of-home placement is the child being placed in foster care. There are many other interventions that an agency can make that can reduce the risk to the child. Oh, I see a question. What are the key variables and features in historical records that are used for training? That's a great question. So basically what the county has done is try to make available all administrative data available. So this is data from interactions with social services, data from prisons and jails, data from, there's also data from like missing data, like partial data on some mental health information, because basically every time that there's an interaction with the system, this is logged in administrative records. And because of the high stakes nature of the task, then for the purpose of child welfare, the agency is able to pull all of this data and make it available to the call workers. And that's the data that has been then used to train the machine learning models. And so this is something like 700 features that are available of information, both of interaction with other agencies and interactions with child welfare itself. Oh, I see that someone shared the details. Yeah, thank you very much. And so there's also work that the county and researchers are doing in looking at how the partial nature of what is observed and what isn't, because not everyone's data is observed, can impact things. And so here what we care about is, well, is the child at risk, which is different to whether there is a risk of out-of-home placement. And so typically, when we're looking at this data generating process, we see the human as this kind of inconvenient meddler in our observational process, right? And often we frame the statistical task as how do we reconstruct why in, for example, sampling bias correction. So what we want to do is kind of get rid of this human meddler in our data. The reframing that we do is there's actually a wealth of discarded information in this data because there's a lot of expertise. And this is not something that is just the case in child welfare, but it is very similar to the type of data generating processes that we have in healthcare, where we have a physician and the physician is making decisions of whether to prescribe a diagnostic test, whether to prescribe a procedure. And so these selective labels issue and both this gap between what we care about and what we observe is something that is common across domains. And so the question is, can we learn from experts' decisions to bridge the construct gap? Infer information about the construct that is relevant to the decisions from experts. One way of reformulating this question is, can we learn from experts' decisions whenever they display certainty and consistency and learn from observed outcomes otherwise? Why expert consistency? Well, in many domains, expert knowledge can be sufficient to correctly and consistently assess a subset of cases while being insufficient for assessing other cases. In healthcare, for example, physicians may be able to accurately diagnose a subset of patients that present well-known symptoms while having a hard time diagnosing other sets of patients. Healthcare professionals, for example, in the context of identifying patients who may benefit from healthcare management programs, may be able to identify certain types of complex health needs that will benefit from these programs, while having a hard time prioritizing among other patients. And in the child welfare context, it's likely that call workers may identify a subset of cases that warrant a house visit, even if out-of-home placement is unlikely, for elements such as there's a history of substance abuse, so we want to visit the home. It doesn't mean that there's a likelihood of that the child will be placed in foster care. And so Here, the idea is, can we learn from expert decisions whenever they display certainty and consistency and learn from observed outcomes otherwise? The question though becomes, how do we learn from experts' decisions? This is something that is very easy to do in domains such as learning from wisdom of the crowds, where we can directly look at the assessment of multiple experts, or multiple labelers. They may or may not be experts, and then directly estimate consistency. In the context of learning from historical data, we often have a single expert making a decision per case. So the question becomes, how can we estimate consistency when a single expert assesses each case? And importantly, there's a known random assignment of experts to cases. This is the case across domains. In the context of healthcare, which patients a physician sees may vary depending on what is their geographic location, what is the insurance that covers their services. In child welfare, whether a coworker works night shifts or day shifts, or whether they work a weekend shift or a weekday shift, that may lead to very different types of calls being observed. The proposed approach is first to model human decisions with machine learning to identify consistency. And then we propose an influence function-based approach to identify consistency across experts. And finally, we incorporate this via a label amalgamation approach. The crucial assumption here is that consistency across experts is indicative of correctness. This is something that may be reasonable in some cases where we say, well, there's a wealth of information contained in experts' decisions. That's why we call them experts. And in particular, expertise may be sufficient for subsets of cases, but not for all. But that is not always the case. So there are many cases in which consistency may reflect shared biases. Consistency may be a result of self-fulfilling prophecies in the healthcare context. And so this is a fundamental assumption that this method is making that should not be taken lightly. And it means that in some cases, we may want to use it, in some others, we may not. And some of the stuff that I'm working on now is also, how can we use this type of approach when we don't want to just assume that expert consistency is something that we necessarily want to learn about. So how do we estimate this? We have the covariates, right? And we have human decisions, and we have observed outcomes, which we may or may not observe. And by training a model to predict human decisions, if this model is calibrated, then we can identify a high consistency set. This is a set in which we can, with high probability, predict the human decision. And this is something that we show is not dependent on functional form assumptions. I'll spare you the technical details, but it's something that I'm happy to chat more about, and the proof is in the paper. The question, though, is, are these high probability predictions reflective of consistency across experts? In other words, are high probability predictions influenced by historical decisions of multiple experts? Or what we're seeing here is just intra-expert consistency, in which there's one expert that is consistently making the same decision, but that doesn't mean that other experts agree. To answer this, we turn to influence functions. What influence functions allow us to do, this is a technique from robust statistics. The local influence method was introduced by Cook in the 80s. And what this allows us to ask is, how will the estimate of a functional vary if weights were perturbed by epsilon? So if the data was perturbed in a certain way. And we can think about all sorts of perturbations. We can think about perturbing the covariate matrix. And we can also think about perturbing the data in terms of the weight that we give to each instance. One specific way of perturbing the data, and this is something that you may have seen, for example, in the context of adversarial learning, where perturbations of a single instance are done to see what are individual instances that can drastically change predictions, right? Here we're looking at perturbations in the direction defined by a set of points. So if you think of these as a high dimensional space where each instance in the training data is in the default assign a weight of 1, you can think about perturbations in any direction in that space that is, let's say we have m points, it's an m-dimensional space. You can think about perturbing the data in any direction there, right? So perturbing only one point is perturbing the data in a direction that is along, like parallel to one of the axes, but you can also do perturbations that are defined by an expert, meaning the set of points that are assessed by an expert. What would happen if we upweight that expert, right? So we're perturbing the data, still just an epsilon, but that epsilon is defined by an expert. And we can estimate the influence. And what this is telling us is how will the estimate of, for example, the predicted probability for a given point vary if the importance given to an expert age was perturbed by epsilon. We can estimate this. All you need to know about this is that everything here, the inverse of the Hessian may be a little bit computationally expensive, but we can approximate it efficiently. And so we can estimate this influence for each expert. And what that yields is, for a given data point, for example, so for a point X test, we can have the influence of each expert on the prediction that the model is yielding. And so if we sort the experts by their influence, what we have here, for example, is a decision maker with influence that is counter to both the algorithmic prediction and what other humans' influence is driving, right? And so once we have this distribution of influence across experts, we can estimate interesting functionals. So we can estimate, for example, the center of mass, which is telling us how many experts are driving the influence, right? So a center of mass close to 1 means that, well, it doesn't matter if we're predicting that humans are making this decision. We're super good at prediction what humans will do. This prediction is driven disproportionately by a single expert in our data. So larger center of mass indicates that more experts are influencing this, but also the direction of the influence matters, right? A positive influence means that the prediction would increase, a negative influence would mean that the predicted probability would decrease. And so we can also look at the aligned influence that would simply give us a number between 0.5 and 1. 0.5 means half the experts are going in one direction, half in the other. 1 means all of the experts are pulling in the same direction. With these, we can revisit our high consistency set. So we used to have just which are the high probability predictions. We can now constrain that set to the high probability predictions that are driven by many decision makers by looking at the 2 functionals that are estimated based on the influence distribution. And from these, we can turn to defining an amalgamated label, where if a point lies in the high consistency set, we learn from experts. If not, we learn from the observed outcome. And this can also allow us to mitigate the selected labels problem, because there are cases in which we wouldn't observe anything, in particular in the context of a positivity assumption violation, where expert consistency leads us to never observe something in a portion of the feature space, and this allows us to populate this portion of the feature space. So what happens when we do this label amalgamation? First, we look at semi-synthetic experiments. And here we look at what happens if we would automate the humans. So this is not really what is being done, but this gives us a reference of what would happen if we predict a model just to train a model just to predict the humans. What happens if we optimize for observed outcomes? That is what is typically being done. And what happens if we amalgamate the labels? That is the proposed approach. And for each of these, we can have a naive evaluation, right? That is what we typically do. And because these are semi-synthetic experiments, we can have the evaluation with respect to the underlying label. So in the case in which we simulate uninformative humans, this is very straightforward, right? We'll just default to the observed outcomes because we're not going to amalgamate anything. There's nothing to learn from experts because they are just random. When humans are oracles, what we see is that we are both, the naive evaluation would miss that, right? We would be very optimistic. naturally, because we would say, oh, what we observe is what we're trying to predict, but that is something that we're, when we take into account the construct that we're optimizing for, things may change. But most interestingly, we see that we're able to incorporate expert consistency and do much better than the label trained to optimize observed outcomes alone. When we have oracle humans, but one human is biased, and there's a non-random assignment that leads to these humans seeing a disproportionate subset of the population that they're biased against. With respect to AUC, well, the performance doesn't look like we're doing better statistically significantly. It's not like a huge thing. But what is really interesting here is that when we look at the performance for the disadvantaged group, the group that this one human is biased against, while all others are oracles, a model that is trained to predict human decisions is like absorbs all of the bias of this one biased human, right? And meanwhile, the amalgamated labels are robust to these. So what we see is that this is what the influence method approach is getting at, is we don't want to just estimate consistency that is driven by a single expert. And so here, well, we see that, yes, we weren't doing much better than the humans in terms of AUC, but in terms of fairness, the difference is huge between just learning from the humans directly and learning in a more robust manner that accounts for whether humans, there's agreement across humans. And so this is some semi-synthetic experiments just to show some basic settings and how the method behaves. And with this, we can turn back to the child welfare context. So after a social worker visits the home, there's out-of-home placement that is the measure that for very good reasons in the county, they've decided to focus on, mostly largely driven by the fact that this is an outcome that has external validation. It's not the same agency, the one that is making this decision. And so that's why they've focused on this one rather than other outcomes that are observed, such as whether there are services that are offered to the family and whether the call is substantiated. However, the availability of these other outcomes allows us to validate the method in a way that we wouldn't have been able to do in most settings, because everything that I've been telling you is about a latent outcome that we don't typically observe. So how do we evaluate this? And so the availability of these other outcomes allows us to look at how does the model behave when we're just optimizing for the observed outcome, right? So with just evaluating with respect to the observed outcomes, this is what we're seeing here. And what happens when we look at the other outcomes? Here, what we see is that with respect to the out-of-home placement outcome, the proposed method is able to do better than the humans, right? So naturally, just optimizing for that is still doing better. This is also the method that we're using in this case, a logistic regression. So one of the things we're looking at right now is what happens when you increase the class complexity, because that may allow the model to do better in both sides. But anyways, here what we're seeing is that the method, the proposed approach is doing better than the humans. And when you look at the other outcomes, what you find is that the method that is just optimizing for out-of-home placement is doing drastically worse in these contexts. And the amalgamated approach improves with respect to this. And so what we're seeing is that there are high-risk cases whose risk is considered by the experts, but is not captured in the target labels used to train a deployed model. And leveraging inferred expert consistency can allow us to build models that mitigate the risk of omitted payoff bias. And so to summarize, and going back to the importance of minding the gap, there's a difference between predictions and decisions. How humans make use of recommendations matters and varies across domains. And while algorithm aversion and automation bias are real, that doesn't mean that humans will always make poor use of algorithmic tools. And we've shown evidence of a high stakes domain in which the role of humans in the loop is both mitigating the risks of having both glitches, but also any form of misestimation, because like these type of glitches are unfortunately not something that is extremely rare. What is extremely rare is for agencies to be transparent about this. And any tool that we have will have errors. And so the role of a human in this loop that can have a discretionary power is important. And second, what we find is that what we show is that the measured construct is different than the relevant construct. And evaluating with respect to the measured construct can be misleading. So just looking at how the human and the algorithm are doing with respect to an objective that we're measuring, that may show us that the algorithm is doing better, but it's hard to differentiate if it's because the humans are poor decision makers or because the humans are integrating other factors into their decisions. And in designing machine learning for decision support, it's important that we center the relevant constructs. And we've shown one direction in which we can give one step towards bridging the construct gap between what we optimize for and what we care about. And with this, I'll pause here and leave the next 10 minutes for questions. Thank you very much, everyone.
Great. Thank you, Maria, for that wonderful talk. We do have some time for questions. So if anybody has any questions, please either unmute yourself and ask a question, or you can leave something in the chat and Maria can answer. So any questions? So maybe I can get started. Regarding the first part of the talk, so I mean, before the talk began, we talked about this work done by Brian Wilder, right? And so just to get a comparison, so you know, in domains in which, let's say, so there are the kinds of machine learning that is done in companies such as Facebook, Google's, whenever they build recommender systems for you. Yes, there's no human in the loop. But whenever you deal with nonprofits, like you are, you more often than not have a human person who's going to look at the recommendation given by the machine learning system and then act upon it, right? Make a decision in reality based on that prediction. So to that end, if the end, so but at the same time, there's this work by Brian which says that I'm not only going to generate predictions and then let you decide on the basis of those predictions. I'm going to directly train my model in a way such that it is optimized to make for the downstream decisions that you or a human being or an expert would likely make. So how does this work? How would you place your work in comparison to what Brian has done? Yeah.
Yeah, that's a great question. So what you're referring to there is the work on learning to collaborate. And so, for example, if I just focus on the cases that are hard for the human, and then I defer to you on the cases that are easy for you, that may lead to better collaboration. And right, there's one variant of this work that we're showing, that is, you can also use the estimating expert consistency as an approach to know when to defer. That is an alternative criteria for deferral, right? One of the things that I would say is fundamentally different in a lot of what I've talked about here and this work is that the work of the algorithm choosing when to defer is assuming that the algorithm has enough observed information to make that decision. And a lot of what I've looked at here is what is the value embedded in the human decision, especially in the first part, for example, where the algorithm is not able to estimate those things about itself, right? So while uncertainty estimation and communication is very important, there are certain things that are just not there for the algorithm. And so that is what we see in the first context, where we looked at how coworkers are making use of recommendations, right? Where we find that they're able to integrate other sources of information in a way that they're just deviating from the algorithmic recommendations in cases in which the score is misestimated because they're successfully integrating other pieces of information, right? Which these are unobserved. This is not something that the algorithm would be able to estimate. Oh, here you do the job, right? And so I think that this gets, and one of the things that I think is super interesting follow-up work here is that this first study that I showed you has the advantage of having inherent field validity. And so we know that there's a high stakes task in which this type of desirable corrective overrides is found. But because it's a field, because it's an observational study, we're not able to know what is the element of the design like that led to this positive behavior, right? So we have a follow-up short paper at a CHI workshop where we identify some of the elements of how the system in the county has been designed that may have led to these positive outcomes. So for example, the fact that call workers have access to a lot of information. And they also have time to make use of it. So there's not a huge time pressure in which they need to make decision, and the faster they make the decision, the better, right? So they have time to make sense of what I think here Natalia Levina's work becomes very relevant on the fact that machine learning recommendations may lead humans to, like, when the machine learning recommendation has something to give, they'll contradict humans' initial assessment. And so the human needs time to make sense of that difference and decide, well, do I go with my gut? Do I adhere to the algorithm? And so I think that one of the elements that is super important of the follow-up work is understanding what are elements of the broader design that enable humans to successfully integrate unobservables in a way that is beneficial to the decisions.
I see. That's very helpful. Thank you. So there's another question by Harvaneet, which is, in the first part of your presentation, what explains the decrease in disparity for the case of human in the loop? Is it the extra information that is not available to the algorithm that humans leverage to decrease error for some groups?
Yeah, that's a great question. So when we see that drop in, like, we see that the deployment of the algorithm didn't increase disparities, but as you're pointing out, what we show is that if the algorithm had been making autonomous decisions, the disparity would have increased. And so what we show through regression analysis is that this is not because conditioned on a score, the likelihood of screening is different across races. So it's not that, oh, the likelihood of a screening for a score of 15 is different if there's a Black child in the associated to the referral or not. That's not what is happening. There's not differential likelihood, but what is happening is precisely what you're indicating here, that is integrating unobservables. And so in this case, the information communicated in the call is something that the algorithm is not observing, leads to other factors being taken into account. And so if we think about it as what are the scores of the pool that is screened in, the composition changes. And changing that composition mitigates that disparity. And so it's, again, very similar to what is driving the corrective overrides, is the successful integration of other sources of information. So we're seeing that the successful integration of other sources of information is both leading to corrective overrides in which humans are less likely to adhere to misestimated algorithmic scores, and it's also leading to mitigating the disparity that would have existed if the algorithm was making autonomous decisions.
Great. Thank you. I think, and Harvaneet replied back saying that he understood. So thank you. Thank you, Maria. I think we're out of time. Unless somebody has any final questions, we can call it a day.
I think I see one raised hand.
There
Nazia?
is?
Yeah, I'm Nazia Malik. I'm doing my PhD in Urban Affairs and Public Policy at Biden School, University of Delaware. I misread the time. I am in the Eastern time zone. I thought it's within the Western, so it would be Central time zone. So I missed major part of your presentation, but I am currently working on my dissertation proposal, and the topic is very much related to the one that you are talking about. I have a question in terms of, the way you're talking about algorithmic, the use of algorithmic recommendation by the call screeners or the frontline workers. My question is that, would the other characteristics or the environmental factors that, for instance, the organizational policies and the intentions or implementation guidelines, in a way they implemented those algorithms, had an impact on the frontline workers' behavior in terms of using that algorithmic recommendation? Second is the behavior. There's a paper by Thea Snow that says that when a human is using algorithmic recommendation and is improving the decision making, it is referred as artificing rather than satisfying. So do you think that humans are mostly artificing, or these frontline workers are artificing, or they are mostly doing the are facing algorithmic aversions or automation bias? So, and the third question is the frontline workers' characteristics in terms of age and experience within that domain, the domain knowledge and experience within that domain had an impact in terms of evaluating the prediction that the risk assessment score is giving in terms of that, and then assessing their own predictions and then making it. How would that be impacting? And the fourth one is in terms of explainability.
Maybe I'll pause you now because I'm gonna forget the questions. Sure. There's just a lot of information. So the first question was how the policies of how to make use of, or at least how I understood it, was how the way in which the instructions were given and the policies were implemented to how to make use of algorithmic recommendations may have impacted the findings here. And that is a super important question that goes back to what I was mentioning of what were the elements of this specific setting that led to, and this may have been the portion of the talk that you weren't here for, to this behavior of corrective overrides that speaks to your second question of what we find the first portion of the talk is that it's not a case of algorithm aversion or automation bias. We do find evidence of what we term corrective overrides. That is the algorithms overriding, being more likely to override misestimated scores. And so in terms of what the instructions were given, I think that definitely is super important. One of the elements here is that the instructions were already given to say that the score is meant to be complementary. And so what we find in terms of humans avoiding errors of omission is something that was at least in the intentions of how that instructions were given was present. And so that was, the call workers weren't supposed to say, oh, the score is low, and so we're gonna screen out this call, right? And so that is part of how the call workers were trained to make use of these systems. What we find in this context is that may have had a positive effect. We cannot differentiate what element of the design is what had this effect, but definitely and this is one of the things that we discussed in this Kai workshop paper, the way in which call workers were instructed to make use of the algorithm as complementary information may have been essential to them actually using it as complementary information and still relying on other sources of information. So that's your first question. The second one was whether there was algorithm aversion or automation bias. And what we find here, obviously this is a spectrum, so it's not like a yes or no, but what we find is evidence that coworkers are in neither of these spectrums, and we do find significant evidence of corrective overrides of coworkers dismissing recommendations that result from a misestimated score. As I said, in particular in the context of avoiding errors of omission. Another question that you brought up was how co-workers' experience may have played a role, and that's definitely, there's a paper that I'm not sure if it's out already, but I know that Alex Sholoshov and Lingwei, who's a PhD student at CMU, Lingwei was working on the heterogeneity across co-workers, so that may be something that you're interested in. one of the elements that is important here is how the fact that co-workers had experience prior to the deployment of the tool may have helped their ability to make really good use of other sources of information. That is an important direction for future work. Whether co-workers who start working once the tool is there are less able to make use of other sources of information, or whether everything's in place so that they learn very successfully how to use these types of information. So the sort of training on making use of unobservables is, I think, a super important direction on a human AI collaboration. And I think I got all your questions, but I don't know. Let me know. I don't know if also we may be a little bit over time, but yeah. Hopefully these answered most of it.
Yeah, you have answered most of it. But I could, we can have this presentation in your paper so that if I would have certain questions, can I email you?
Yeah, and the papers are available online. So both the Kai paper, and we recently made the working paper that does the extended analysis on disparities available on SSRN.
And also, Nazia, the recording of this seminar is going to be available on the center's website. So if since you missed the first half of the talk, you can go back and watch that recording. And if you after that, if you have any questions, I'm sure you can follow up with Maria.
Thank you so much. Thank you.
Great. Thank you, everybody. Thank you, Maria, once again for taking time, to share your wonderful work with us, and certainly very informative for me. And yeah, I guess we'll call it a day. Thank you, everybody. Bye, Maria. Thank you.
Thank you, everyone. Bye.
Bye. Have a good day.